Hello, I'm Carlos Meri Celma, Chartered Architect and Structural Engineer, and I will be presenting the paper on Performance of Structural Grids for Tall Buildings based on Geometric Islamic Patterns that has been written in collaboration with David Gallardo and Carlos Lazaro, Associate Professors of Structural Engineering at the Universitat Politecnica de Valencia. Geometric patterns, inspired in the Islamic tradition, are visually attractive and a source of inspiration for new structures. However, they come at the expense of complex structural behaviors, making it hard to provide general rules when using technological applications. The goal of this paper is to assess the structural feasibility of such grids, comparing their in-plane performance against the conventional diagrids. In a previous research carried out by the Universitat Politecnica de Valencia in collaboration with the Technische Universiteit Delft, we studied the in-plane behavior of 20 common historic Islamic patterns. The three stiffest, or best performing patterns from that study have been selected for this paper as potential candidates to become a feasible alternative to conventional diagrids. They are, by decreasing degree of performance, 1. The Yesil Mouse, 2. Has-Behest, and 3. Lahore 4 patterns. Additionally, Al-Nasir and Fatehpur Sikri patterns, 4 and 5, are included as well. They are chosen only by their appearance, and will show what to expect when only aesthetics are considered when choosing a pattern. These 5 patterns, together with the conventional diagrid, are mapped into a given tall building in a study case approach. The tower volumetry is inspired in the 90 stories and 360 meters high building used by Monturian and Gelucci studies on hexagrids and Voronoi tessellations. Nevertheless, as the different patterns have different modules and proportions, the building plan adopts the circular to ensure the structural continuity and minimize the discretization effects in the results. Also, a centric circular concrete core is introduced for realism, helping to mitigate the inter-story drift at the recess location. The steel member's total length is aimed at 15 km in all cases, to ensure the grids have a similar scale and that the cross-sections are within the same range for a similar performance. Details on the module sizing, orientation, analysis consideration, and loads can be found in the full paper. Regarding the design philosophy, we understand the main reason for choosing a grid inspired by the geometric Islamic tradition is its unique appearance. Therefore, the aesthetics is another factor that should be part of the design process. In this regard, in order to achieve a uniform view of the facade grid from all locations, the grid is composed of rectangular hollow sections with constant external dimensions, depth and width, in the whole building height. The depth and width change for each tower, but in any given building what changes is the cross-section thickness. This design choice leads to solutions that could be further optimized, but since all towers are designed with the same approach, the relative behaviors for the final comparison should stand. The beam depth is increased in steps of 300 mm, and the beam width is always 2/3 of that depth. The thickness varies according with the requirements at that location, rounded to the closest conventional plate thickness with an upper limitation of 1/20 of the depth. With these proportions, the depth is defined by the ULS demand at the worst location. So, the grid is sized for ULS and checked for SLS, with a basic witness speed of 30 meters per second. Going to the results, pattern 1, inspiring the Yesil Mouse, behaves very similarly to the conventional diagrid, and can be easily used as an alternative to it. In fact, it can be considered as a variation of the conventional diagrid, with the horizontal elements meeting a half diagonal instead of at the nodes. Although the tonnage required is similar, the measured drift at the top is slightly bigger for the pattern, making the overall performance slightly worse than the conventional diagrid. It doesn't come as a surprise that it has been widely used for cell structures by architects such as Shigeru Ban. On the other hand, probably its biggest limitation is its constructability, since this pattern requires 3 times the number of nodes of the conventional diagrid. Patterns 2 and 3, inspiring Has-Behest and Lahore 4 complex, were selected because the good behavior they showed in a previous study. Pattern 2 required a grid tonnage per square meter of building surface approximately 50% higher than the conventional diagrid, but is also stiffer with smaller measured drifts at the top. With those two parameters and combined together in the efficiency comparison graph, pattern 2 is just 12% less efficient than the conventional diagrid. This is a difference that might be acceptable in the case of iconic landmark. However, from the constructability point of view, pattern 2 is the one studied with the highest piece counting and number of nodes, making it even more expensive. Pattern 3 results in a similar tonnage per square meter to pattern 2, as was expected when they were selected. However, its increased flexibility reduces relative efficiency to 66% of the conventional diagrid, a value too low to be considered as a suitable alternative. Lastly, patterns 4 and 5, in Spatial, Nasir Muhammad and Fatehpur Sikri, were chosen just because their aesthetics. As a result, the required tonnage and measured drifts at the top spread through a wide range of values. We have from kind of light but very flexible behavior in pattern 4 to a very heavy but at the same time robust and stiff behavior in pattern 5. In any case, when both parameters are combined together, the result is that both grids display a relative efficiency of just 1/3 of the conventional diagrids. This renders them unsuitable for structural application and highlights the importance of looking beyond aesthetics when choosing an Islamic pattern for reference. To conclude, there are some recommendations I would like to share. Choose the right pattern, scale, and orientation. This paper shows some examples, but in our previous study there is a wider compilation on how the most common historic patterns behave and compare. Be aware of the load paths in an early stage. Kinks and turns in the load path introduce big bending moments and concentration of stresses at those locations. And finally, be creative and have fun. Load paths can be closed or improved filling the stars, extending the beams, or just addressing the stress peaks locally. Creativity thrives under constraints. Thank you for your attention. If you have any questions, we will be pleased to answer them.